Okay, for question 2 of the assignment, we're supposed to use a Born-Haber cycle to calculate the lattice energy of zinc oxide. So Born-Haber cycle, you recall the acronym F, A, I, L. F stands for formation, A stands for atomization, I stands for ionization, and last but not least, L stands for lattice energy. Okay, so this is what we need to find, the lattice energy of zinc oxide. So quick recap of the aim equation. The aim equation will involve Zn2 plus gas plus O2 minus gas to form ZnO solid, and that's your delta H lattice. Okay, so that is our aim equation. So you're given a number of enthalpy changes. It's important that you write down equations, right? So if you realize that this information here that's given to you is grossly insufficient because you only have EAs of oxygen, and then you're basically starting from elements. Alright, so you're starting from zinc solid and half O2 gas. The end goal is to come to a process where you can get your Zn2 plus gas and O2 minus gas. So you need to definitely to also consider ionization energy of your zinc. So first IE and second IE of zinc, and this can be found in the data booklet. You also need to consider the breaking of the oxygen-oxygen bond. So in O2 you have a OO double bond. You need to break half of it, which means you need half of the bond energy of the OO double bond. So in this case, from the data booklet, refer to the bond energy of OO double bond, you have 496, and since in this case you're only forming one oxygen atom, you need half of the bond energy. Okay, so let's just look at how we apply. First thing first, to draw a Born-Haber cycle, because it's an energy level diagram, indicate the energy axis. Then start with a reference point. Alright, typically I put my 0 and then I'll include my elements. Okay, so in this case, the elements involved are your zinc solid and half oxygen gas. So from there, we can apply our acronym of FAIL. We do our formation first. So that's our formation. So delta HF formation of ZnO, which is 1 mole of zinc oxide solid, formed from its element zinc solid and oxygen gas, half mole of oxygen gas. So that's a formation. Once you're done with our F, we can move on to the atomization. So F stands for your formation. Okay, over here you can take the time to also write down the values. In this case, the formation of zinc oxide is negative 348. So I'm going to use green to write down all the enthalpy changes, negative 348. Okay, now we move on to atomization, which is A. So atomize, you need to both atomize the zinc as well as the oxygen atoms. So consider atomizing zinc first, and that is given as your value of atomization of zinc, positive 130. So similarly, positive 130. So you can either write this notation, so you can write the value. Okay, so in this case, what happens? Your zinc solid now becomes your zinc gas. So the whole process of atomization is to form gaseous. Alright, atomization is always to form gaseous atom. Okay, so 1 mole of zinc gaseous atom formed. Now, in this case, after I'm done with atomizing zinc, I need to atomize oxygen, because now it still exists as molecule O2. So consider atomization of oxygen, which is, as I mentioned earlier on, it's the half bond energy of OO. Because for OO covalent bond, when you break it, bond energy, you get 2 oxygen atoms. Okay, now I only need 1 oxygen atom. You can see, right? I only need 1 oxygen atom, because 1 zinc oxide only contains 1 oxygen atom. So I therefore only need half a mole of OO to get only 1 oxygen atom. So that's why half bond energy. In this case, the value is half of positive 496. So in this case, I'm done with my A, atomization of both my zinc and oxygen. Okay, so atomize both my zinc and oxygen. Now I consider forming, after I form gaseous atoms, I now form gaseous ions. So I need to form ions for both Zn2 plus and O2 minus. So first of all, I can consider IE. Now I can combine steps that are similar into one step. For example, first and second IE. So first and second IE of zinc, basically you're removing 2 moles of electron from the zinc gaseous atom to form Zn2 plus gas, 2 electrons, and your oxygen atom remains, so 2 electrons. So in this case, the value, okay, this can be found from the data booklet, plus 908 plus 1730. You get 2638 kJ per mole. Okay. Then once I've done my cation, gaseous cation, and this is my ionization, right? I need to now get my gaseous anion. So focus now on the gaseous anion. So I'm going to combine the electrons from the zinc that's lost from zinc to form Zn2 plus with oxygen to form my O2 minus. So the end goal is to get Zn2 plus gas plus O2 minus gas. Alright, O2 minus gas. So as I said, this is the final state before you can use a lattice energy. So consider the first EA of oxygen. So first EA, basically you form O minus gas. Alright, and then now you can see one more electron is used up. And then you get O2 minus. This is second EA. Okay, and then it goes all the way down to your delta H lattice energy. Okay, because there's a definition of lattice energy. So in this case, the energy cycle is worth 3 marks. Okay, any mistakes or any equations that's not correct, I will penalize you once each. Okay, so in this case, the brown arrows are all the clockwise arrows, whereas the green arrow with the formation arrow is the only anti-clockwise arrow. So again, the acronym, right? F, A, I, this is also I, your EA is also forming ions, and last but not least, lattice energy, L. Alright, so apply your Hess law. Formation, which is F, alright, it's only anti-clockwise arrow, will be equals to your atomization. So is I's ionization energy, first IE, second IE, first EA, second EA, and then plus the L. Okay, so similar to tutorial what we do. Alright, so F, formation, atomization, all of these are your atomization. Then your ionization, the form ions, and then the lattice energy, L. And submit the values, solve for your lattice energy. Your lattice energy should be highly exothermic. Why is a lattice energy highly exothermic? Okay, because you expect this process to release a lot of energy. Why so? Because you are forming very strong ionic bonds. So forming strong bonds, it releases energy, and therefore this is going to be exothermic. Okay, so that's your bond neighbor cycle. Okay, for those of you who need to copy this down, you can consider pausing the video. I'll move on to part 2. Part 2, basically we're supposed to compare the stability of calcium oxide to that of ZnO. So in this case, O2 minus, Ca2 plus, Zn2 plus, and O2 minus. So in this case, the anion is the same. We can safely omit the analysis. We are now just comparing between calcium and Zn2 plus. Now, so in this case, if you take a look at it, it's a ionic compound. So basically, we are comparing the stability, right, which is with regards to the ionic bond strength. And ionic bond strength, we know that we will look at delta H lattice energy. So in this case, delta H lattice energy, this formula is not foreign to you. Q plus Q minus over R plus plus R minus. So in this case, the charge of calcium and zinc are the same. Alright, O2 minus is the same. So the only thing that differs is the size of your cations. So the question is, how do I know which size is bigger? Whether is it calcium 2 plus or zinc 2 plus. So this one you can refer to your data booklet. The values of your calcium 2 plus and zinc 2 plus is given to you. So it turns out that calcium 2 plus is bigger than Zn2 plus. So in this case, calcium 2 plus is bigger. The lattice energy of calcium oxide will be in terms of magnitude. So again, the modular sign is important. The magnitude of calcium oxide will be smaller than that of zinc oxide. Okay? Or in other words, if I were to write it, lattice energy of calcium oxide is less exothermic than zinc oxide. Okay, this will imply the ionic bonds in calcium oxide are weaker, and as a result, calcium oxide is less stable than zinc oxide. Okay, moving on to B. For B, we have standard change in entropy and standard enthalpy change. This value here, entropy change here. So the question now asks you, why is the change in entropy positive? So in other words, why is delta S more than 0? Okay, so in this case, you can see the reaction. You have 0 moles of gas. At the end of this reaction, you have 1 mole of gas. So again, why do I focus on gas? Because this is a reaction, I cannot use change in phase. So over here, I'm looking at if there's any change in number of moles of gas. It turns out there is. So keyword, there is an increase in number of moles of gas. You want to use molecules or particles are both accepted, but you need to tell me specifically, alright, what's the change? So from 0 moles of gas to 1 mole of gas. Okay, and therefore there are more ways to arrange particles, increase disorder, increase entropy. Alright, so you're going to make your answer complete. This is consider what you can do. Okay, last part of question 2 is to calculate the minimum temperature for the decomposition to be spontaneous. So in order for this reaction to be spontaneous, your delta G has to be less than 0. Alright, so this is condition. And we know that delta G is delta H minus T delta S. We have the delta S value to be 174 J per mole per Kelvin. We have the delta H value to be positive 71 kJ per mole. So all we need to do is substitute into this equation. The only thing you need to take note is to have units parity, because this is in J per mole per Kelvin, this is in kJ per mole. The magnitude of the joules of energy is different. So as a result, to me, it makes more sense to convert the delta S into kJ. So that's why I divide by 1000. Alright, so let's convert J per mole per Kelvin to kJ per mole per Kelvin. Alright, so that your delta H is of the same units, kJ per mole. And then when you divide, the units can cancel out and you end up with having a Kelvin. Okay, so the minimum temperature will be 408 Kelvin. Alright. Some of you all get 408.0 something, you round out to 409, just take note, right? We typically present our answers to 3SF. So 408 Kelvin is good enough. Okay, with that, we are done with the corrections for question 2.